Hi, everyone. Hello to all of my AP Computer Science Principles people out there. I'm excited you're back for another review so we can hit the hot topic of the internet. So, welcome back. I'm Sandy Chaika from Riverside Brookfield High School, just outside Chicago, Illinois, and we are here to review and get ready for the APCS Principles exam. So, what is going to happen today? Well, we always want to know, what are we going to learn? Specifically, we're going to cover all of Big Idea 4 today. That is the internet. It includes how computing devices work together in a network, explain how the internet works, as well as explain how data are sent through the internet via packets, and the differences between the internet and the World Wide Web. The second big learning objective is 4.2, and we are going to focus on fault tolerant systems like the internet, describing the benefits of fault tolerance, explain how a given system is fault tolerant, and identify vulnerabilities to failure in a system. And last but not least, we're going to look at parallel and distributed computing, specifically looking at sequential, parallel, and distributed computing, comparing their solutions and determining the efficiency of solutions. The skills that we will mostly cover today include evaluating solution options, explaining how computing systems work, and all of this comes back to what's going to happen on the exam. So, this particular big idea, since we're covering all of it, I can tell you it's 11 to 15% of the AP exam weighting. There's a potential for single select multiple choice questions, as well as multi select multiple choice questions. Multi select are at the end of the exam, the last 8 questions where we say select 2. So, our agenda for the rest of the review is to just basically discuss the internet, review vocab and essential knowledge, discuss parallel and distributed computing, and of course, review more vocab and essential knowledge, do some multiple choice question practice, and of course, we're going to end with a create performance task tip of the day. So, let's start out with a little review of vocab. So again, I really believe that you want to make sure you understand what different terms mean. So when they come up within a question, it's not the words or the meaning of the words that are keeping you from answering the actual question. So a computing system is a group of computing devices and programs working together for a common purpose, not just the internet, any system. A network is a group of interconnected computing devices capable of sending and receiving data. So it's going both ways. So a computer network is a type of a computing system. So remember, a network is a type of system. We also are going to look at the fact that we have paths. The sequence of directly connected computing devices from a sender to a receiver is a path, even if it doesn't go in a straight line. Routing is the process of finding a path from the sender to the receiver. And bandwidth of a computer network is the maximum amount of data that can be sent in a given amount of time. Usually, this is measured in bits per second, or BPS. Bandwidth often is what affects us when we have many people all on the same system. So sometimes if a lot of people in your home are all using the internet, and especially if they're all trying to use video conferencing at the same time, you might find out that you don't have enough bandwidth because it can't send everything in the right order or at the speed, keep up with the speed of it all. A very, very important term with the internet is protocol. Protocol is an agreed upon set of rules that specify the behavior of the system. So it's something that has to exist in order for all of this to work. Internet protocols are open, meaning everyone has access to them. That's really important so that it doesn't matter what type of device, what brand you have, all of the protocols have to work together no matter what you have. IP is short for Internet Protocol. TCP and UDP are common protocols used on the internet. Scalability is the capacity for the system to change in size and scale to meet demands. So, in other words, we want to have scalability. So, if more people want to be in our system, we can make minor changes and not interrupt or stop everything in order to accommodate a larger change, a larger amount of people or devices. Packets are small amounts of data sent over the internet. They contain data and metadata, including the sources and destination, as well as data needed for reassembly. And here we go, World Wide Web. Let's stop for a moment here. This is a system of linked pages, program, and files. HTTP is a protocol that's used by the World Wide Web. Now, this next statement might be one of the most important things for you to remember. The World Wide Web uses the internet. They are not synonyms. The World Wide Web uses the internet. They are not the same thing, even though a lot of people act like they are and use the words interchangeably. That's not correct. Redundancy is the inclusion of extra components that can be used to mitigate failure of a system if other components fail. So redundancy is when you have extra things available. So if one thing doesn't work, the others can pick up the slack. Sometimes you might do that when you are putting together maybe a fundraiser or maybe some activity at your school. You might have more people than you need. So that this way, if someone is not able to participate at some point in time for whatever reason, you have someone else who can take their place and you don't have to stop the whole process. A system is fault tolerant when it can support failures and still to continue to function. We use redundancy to help us establish fault tolerance. So I want to take some time to look at some visuals and actually look at some examples and simulations of the internet. So we're going to start off by taking a look at how information might travel on the internet or what's the process. So when something is going to go across the internet, is going to travel through the internet, we start out by taking a file, whatever that is. It could be images, videos, audio files, or just plain text. A lot of different things can travel over the internet, but often they are too big to all travel together. So in order for the internet to work, the files, whatever type they are broken down into packets. So I might have one large file here, and I'm sending that to some other destination via the internet. So the first thing the internet, the protocols do is break down the files into packets. And so this now, when I put these all back together, I can make the original file. The packets have to come together at some point to make the original file. Now, each packet has a header and data. You don't necessarily need to know this header and data, but you do need to understand the concept. So the header has information about the routing, including the source IP address, the IP address of the device where the file is starting from, as well as the destination address. So where is it going? And then there might be other information needed to route the packet or to put the pieces back together. So this has got a lot of data about the file. And then the data part actually has the pieces of the file that are being sent in that particular packet. I kind of think of the header as the envelope if I were sending something in what we now call snail mail. So, in case any of you ever actually get a letter, it often comes in an envelope, and the envelope has things like your address. There might be the sender's address in the corner in case something happens, it can get sent back to the sender. There might be other information where it needs to go. The post office might put extra information or data on there or codes on there to help it move through the process of getting to the destination. The information that you're ultimately interested in when you receive the letter is what's inside. That's the data, that's the fun stuff. Unless it's a bill, then it's not so much fun. But that's the part that actually is the message for us. Now, packets are sent from the source computer to routers, and the routers look at the IP address of where they're going until they find where they can get to the final destination. So it starts somewhere, goes through some routers, we don't know how many, could be any amount, and ends up at a destination. Now, you might be looking at this going, I've never seen the internet look like this. And that's because it doesn't look like this. The internet is a web, it is going in all different directions. In other words, we have to change this because what if a router shuts down? Or what if one path gets damaged? Does that mean there can be no communication? Or what if there's a traffic jam? Believe it or not, we can have data traffic jams. So it might look a little more like this. So we still have our source destination that's sending the file, and our source computer that's sending the file, and our destination computer that's receiving it. And there might be a whole lot of different routes to take. In theory, these routes could go different ways. There might be going in different directions. But this way, if one router were to disappear, we could move around through the other routers and still get to where we are going. So we don't know exactly what it always looks like, and they don't always take the same path every time, even if there always is the same source and the same destination. Here's a fun little simulation of what it might look like. Bear with me. Each of these rubber ducks is a separate packet that together contains the entire file I am sending. I want the file to end up with this receiver. And each of these squares or rectangles is a router. We have different paths that the ducks can take. So I'm going to send the ducks on their way. Here they go. Ooh, all different directions. Definitely not direct paths. But it appears they ended up at the receiver. But I'm not sure what order they came in at. I'm not sure did they all get there. So that's why we have something called TCP, or Transmission Communication Protocol. This is going to check to see what was received and what order it should go in. So part of that header probably had information about the order. So TCP has figured out from the information that there should be 3 packets and the order of those packets. So it's going to do a checklist. Did packet 1 come in? Yes. Packet 2, it's there. And packet 3, woohoo! So TCP says all is good and everything worked out fine. Now, sometimes it doesn't happen that way. Sometimes we send our ducks in the way. Uh-oh, two, where are you going to? Oh, poor ducky number 2 doesn't appear to have made it. Will our receiver know that? Well, our friend TCP comes out, knows it has 3 packets, checks for packet 1, checks for packet 2, checks for packet 3, and so TCP sends a message back to the sender, send 2 again, we need 2. And the sender will then resend 2. Now, let me be clear, this is all happening without me as the human being intercepting anything or doing anything. This is all using internet protocols and it's all been established. So it's all happening kind of behind the scenes and often so fast we don't even know it happened. Now TCP will check again. 1 was already there. 2 is there now. And here's 3 now. All is good and we can move on. Now, one of the things we're looking at here is a lot of routers with many paths. And so one of the things becomes, well, what happens if we lose a path? So I just lost this path here. Well, that's okay because I have other paths that can move out to other routers. So even though I can't get directly to this center router here, I can go through either one on the side and eventually get there if I so choose. Well, we just lost another one. Well, that's okay. I can't go directly from the router up here to the router down there, but packets can go around and get to either one of those still. So we still have fault tolerance. This redundancy has helped us. Yep, something else happened. Another path went down. Well, I'm minimizing my options, but I still can get to every router in some way, shape, or form. I'm minimizing my choices. The packets will not have as many options, but they can still get everywhere they might need to go. One more went down. Now, this looks like we're dead in the water, but we're not. Even though this little router really isn't going to be very helpful, if something ends up there, it can just send it right back here to the router on the bottom, and then this router can get it moved over, or if we're going back, it's fine. Now I have a problem. This path has completely cut us off. I have no way of getting to the router right before the receiver. So now I've lost my fault tolerance. But because of redundancy, we had to eliminate several paths before we actually lost that fault tolerance. And the idea is that hopefully they would happen not so close together that you could repair one before another one would happen. There's never a guarantee. But for the most part, we usually have pretty significant good internet service. All right, so that's some of the vocab for the internet. Let's talk a little bit about different types of computing. So, back to our vocab, sequential computing. This is a computational model in which operations are performed in order one at a time. So, we do step A, and then B, and then C, and then D, and then E, and so forth. We cannot start the next step until the previous step is completed. The time it takes is as long as it takes each individual step. So we have to see how long it takes each of the steps and add that all up. Parallel computing is a model where the program or whatever the task is broken into multiple smaller sequential computing operations, and some of them are performed simultaneously. Now, not all things can work this way, but when they can, it can help save time. So normally this is about different processors on the computer, each taking on different jobs, some of them being simultaneously. The time takes as long as its sequential tasks, plus the longest of the parallel tasks. And we're going to look at an example, so don't panic if you're not quite sure what all of this means yet. Distributed computing is a model in which multiple devices are used to run a program. So we don't just have multiple microprocessors or processors in the computer, we have multiple computers, maybe in different places. There's a term called speed up, and the speed up of a parallel solution is measured, and the time it took to complete the task sequentially divided by the time it took to complete the task when done in parallel. Again, we will look at an example of this in a few moments. All right, let's look and talk a little bit more with examples about these different types of processing. So, what are some tasks that can be completed sequentially? Let's just stop and think. Is there anything I know of that happens one thing at a time? One happens after the other, and I can't go any faster. I can't get to step two until step one is done. Well, an idea I have is for most of us at least, maybe there's exceptions, our school day. We attend one class at a time. So for me, I have period one, and when that's over, and only when it's over, I can start period two. And when that's over, and only when it's over, I can start period three, and so forth. I can't do two classes at the same time. Now, for some families, preparing a family dinner might be a sequential process. Maybe there's one person who's doing all the cooking, and maybe they'll do it so that first they'll make the salad, then they'll make the potatoes, then they'll make the meat, and then they'll make the dessert. That may or may not be the best way, but if you're like me and you're not very good at cooking, it's probably the safest way. You don't want to have too many things going at one time. Often, when we follow directions to build something, even if it makes us frustrated, we need to follow the instructions sequentially. So maybe I am putting bikes together for to donate to a charity for little kids. And so I know these small children are going to be excited to get their first bike. And so I have the pieces and I have the instructions. And I have to follow the instructions one step at a time and hopefully come up with a bike at the end. Now, maybe these have to be done sequentially, or maybe there's some ways that we could do some of these in a parallel manner. Well, at least at my school, the school day is not going to change. Like, I'm not going to be able to do multiple classes at the same time. Maybe some of you have a different situation. I don't know. But for me, we'll still only be doing one class at a time. So that's going to stay sequential. But a family dinner could be done in parallel and not just by one person. So maybe multiple people could pitch in. Hint, hint to all you students out there. And each one could be preparing a different dish for the dinner at the same time. And this way, dinner will be completed a little more quickly. Well, putting together bikes, if I'm trying to put together 10 different bikes, I'm going to have to do them one at a time. But if I could get some friends to help me, we could all be doing the bikes at the same time, putting together the bikes at the same time. And so if I have 10 friends, we can each put together one bike at the same time, or maybe five of us can do it all at the same time. So each one of us will do two bikes at the same time. That's really going to cut my time immensely. So you might be thinking of some other ideas, but what about in a distributed manner? Well, again, since the school day is not going to happen parallel, it's not going to happen distributed, at least not the way in the situation I'm describing. There could be other ways it could happen. But dinner, how about a potluck dinner? If you're not sure what that is, that's when you might have several people over from different places, but everyone brings something to just to contribute to the meal. So maybe I ask one of my friends to bring the bread, and maybe another friend is bringing the salad, and maybe my cousin is bringing the potatoes, and maybe someone else is bringing the vegetables, and maybe I'm making the main course of either meat or fish or a vegetarian meal, and maybe someone else is cooking and bringing the dessert. So they're all doing it in their different homes. We might all be doing it at around the same time in parallel, and then we bring it all together to have in one place and share together. If I'm just doing the bikes for a local charity, maybe it's not going to be distributed, although I could have people do it all at their own homes. But maybe someone heard about this wonderful organization and they want to build it up nationwide. So now we might coordinate bike building all over the country. And instead of being able to just build 10 bikes and donate to one place, we might be able to build hundreds or thousands of bicycles. So that's just a little bit of an idea just to kind of get you thinking. I'm going to share a more specific example that's kind of near and dear to my heart: grading computer science tests. How about the practice performance task? Ooh, those can be time consuming. So I have some sequential steps I need to do. First, I have to determine the scoring rubric. Let's just assume that takes me 60 minutes. Then I can score the first task, and maybe that one takes me 10 minutes. Then I score the second one, and it takes 15 minutes. The third one takes another 15 minutes. The fourth one takes another 20 minutes. The fifth one takes another 10 minutes. And the last one, or the seventh one, I'm sorry, the sixth one takes me 20 minutes. So I have determining the rubric or learning it, and then scoring 6 tasks. By myself, I can only do these one at a time, and it will take me 150 minutes in total to grade these tests or tasks sequentially. Over 2 hours. But I have a lot more to go. I need to find a better way. So I decide, maybe I can get some friends to help me. Granted, they have to be some pretty good friends who are going to want to help me do some grading, but I think I might be able to convince some people. I'm still going to need to determine the scoring rubric, which took the 60 minutes. I still have to set that up. But then my friends using that rubric can help me score, and we can all do it at the same time. So one person gets tasks 1 and 2, one gets, 3 and 4, and one gets 5 and 6. So let's take a look at this. How long would this actually take to complete now? So let's just pause and think. Well, I'm still going to need to do 60 minutes of work to start with, no matter what. But then all 3 graders can start at the same time. This first grader needs 25 minutes to complete both tasks. The second person grading needs 35 minutes, 15 plus 20. And the third person grading needs 30 minutes. So 25, 35, and 30. So it won't be totally done until the last person is done, which means when person who's scoring 3 and 4 end. They took 35 minutes. So the total amount of time it now has taken by working together is 95 minutes, because we still have the first 60 of getting the rubric situated, and then another 35 minutes before everyone is done grading. So that's a total of 95 minutes if we work in parallel. Not too bad. Better than 150 minutes that it would have taken me all by myself. I'm kind of happy with that. So remember we talked about the speed up. Remember I said the speed up is the amount of time it took to complete the task completely sequentially compared to the maximum amount of time it would take using a parallel solution. So for this particular example, my speed up would be 150 divided by 95, which comes out to be 1.579. So I just wanted you to have an idea of how this might work. Now, in essence, this is kind of how your performance tasks do get graded, only we take it one step further and use distributed grading as well. So first, people work on the rubric, and nothing can happen until that rubric is finalized. And even though you have the rubric, we also have to make sure that all of the people grading are thoroughly trained so they all use the rubric correctly. That's going to be step 1 of the sequential task. And then some people will be in one location, others might be grading from home, and that'll all be running parallel, some in the same location, but then distributed also in other locations. And that's how we get thousands and thousands and thousands of create performance tasks graded on time. Just a little peek behind the curtain. All right, so we've talked a lot and given some examples. Let's actually take a little time to practice. So these questions, we're going to do a few questions together here. They are from AP Classroom. Which of the following best explains how messages are typically transmitted over the internet? A, the message is broken into packets that are transmitted in a specified order. Each packet must be received in the order it was sent for the message to be correctly assembled by the recipient's device. B, the message is broken into packets. The packets can be received in any order and still be reassembled by the recipient's device. C, the message is broken into two packets. One packet contains the data to be transmitted, and the other packet contains metadata for routing the data to the recipient's device. D, the message is transmitted as a single file and received in whole by the recipient's device. Feel free to pause the video and read through this in a little more detail. Make sure you feel confident with your answer. When you're ready, start the video again and we'll go over the answer. All right, I hope you're ready for the answer. And it is B. So I'm hoping some of the examples I showed you might have helped you to visualize it a little better. So maybe you might remember this. So let's look at what B said. The message is broken into packets. So that was like our little duckies. The packets can be received in any order. Those ducks were all over the place. It didn't matter who finished when. And it was still reassembled by the recipient's device. Remember, TCP took care of that, right? What's wrong with A? The message is broken into packets and transmitted in a specified order, and it must be received in order. Well, we don't have to do that. TCP takes care of it for us. C, the message is broken into two packets. One contains the data and the other contains the metadata. Well, this is sort of referring to the two parts of a packet. We have the data, the information we're sending, and the metadata was like the header part, right? Like the envelope. But that's in each packet. The message could be broken into any number of packets. The message is transmitted as a single file and received in whole. Well, honestly, most things are just too big for that. So that normally does not happen. All right, let's try another one. Which of the following best explains how fault tolerance in a network is achieved? A, by providing high bandwidth connections between devices, enabling data packets to be transmitted as quickly as possible. B, by providing multiple paths between devices, enabling routing to occur even in the presence of a failed component. C, by providing open network protocols, ensuring that all devices on the network are interacting in a standard way. And D, by providing software to monitor all network traffic, ensuring that data packets are sent and received in the proper order. Once again, I encourage you to pause the video, really read these carefully, and think about what each one says before you decide on your answer. All right, I hope you're back after really reading and you came up with an answer. So ready? Here we go. The answer is B, providing multiple paths between devices, enabling routing to occur even in the presence of a failed component. So that's why we don't go in a straight line. That's why we had multiple paths and multiple routers. And remember, we had some of those paths disappear or break down, and we still kept fault tolerance for quite a while. Let's look at these other answers. High bandwidth will help with speed, possibly, but that's not helping us with fault tolerance. If I have high bandwidth, but still only one path, that's not helping me keep fault tolerance. By providing open network protocols, ensuring all devices are interacting in a standard way. Well, we need this for the internet to work, but this in and of itself does not give us fault tolerance. This is how we just have an internet working with all different types of devices. By providing software to monitor all network traffic, ensuring that data packets are sent and retrieved in the proper order. Well, this is helping. This is like a TCP type thing they're talking about, where we are making sure that everything is sent and received and we can put it back in order. But that again does not help with fault tolerance. We could have that with a straight line of routers, But if one path would go out, even though we have the software, it would not be fault tolerant and our internet would break down. All right, let's try another one. Which of the following best describes the ability of parallel computing solutions to improve efficiency? Any problem that can be solved sequentially can be solved using a parallel solution in approximately half the time. Any solution can be broken down into smaller and smaller parallel portions, making the improvement in efficiency theoretically limitless as long as there are enough processors available. C. The efficiency of parallel computing solutions is rarely improved over the efficiency of sequential computing solutions. And D, the efficiency of a solution that can be broken down into parallel portions is still limited by a sequential portion. There's a lot of words here, so don't be afraid to pause your video, take some time to read it, and come back when you think you have an answer. All right, here we go. The answer is D, lucky D. So the efficiency can be broken down into parallel portions. So, like when I gave three of my friends the CS tests or tasks to grade, I broke that down into parallel portions. Each one was grading parallelly at the same time. But it was still limited by the sequential portion of, first of all, the initial 60 minutes that it took me to actually come up with the rubric or maybe train them on the rubric. And it was also limited by each one of my friends still had two tasks or tests to grade. So what I had to realize there was that they were doing sequential things with at parallel times. So that's why we had to make sure that when we calculated the total amount of time, we took into account the total amount of sequential time each person took. Now let's look at the other answers. Any problem that can be solved sequentially can be solved using a parallel solution in approximately half the time. Well, that's not true. Some things that are solved sequentially, there might not be an option for parallel. There might not be any way to do the different pieces unless other pieces are already done. Any solution can be broken down into smaller and smaller parallel portions, making the improvement in efficiency theoretically limitless as long as there are enough processors. Well, that's not really true either because, again, we still have some sequential parts that might exist. So we cannot necessarily break it down anymore, or we might just be breaking it down so much that it might end up where things are not done in correct order ultimately. Parallel computing solutions is rarely improved over sequential. Well, that's not necessarily true. We saw an example where that could easily make it more efficient. So it just depends on the problem and the situation. So the main thing with these first three is this is kind of like an all or nothing in certain ways with some of these. So be careful when you're reading that you really think about, is there a counter example to this statement? If there's a counter example, maybe that's not the right answer. All right, another question. A computer has two processors that are able to run in parallel. The table below indicates the amount of time it takes either processor to execute four different processes. Assume that none of the processes is dependent on any other processes. So we have each of these process W, X, Y, and Z. And the execution times are 20 seconds, 30 seconds, 45, and 50. None of these need to be done sequentially. A program is used to assign processes to each of the processors. Which of the following describes how the program should assign the four processes to optimize execution time? So don't worry, I'm going to put the table on the slide with the answers or the options for answers. So here's our table. It's the same table. So what we're looking for is which two. So I'm going to give one processor two things to process, and the other processor, the other two to process. So I'm going to let you read through. Should we do it as WX and YZ, WY and XZ, WZ and XY. Um, or Z should go to one and WXY should go to the other. This probably is going to really need you to pause the video here. I definitely would not be able to do this one in my head in this amount of time. So pause the video, analyze it, and see what you come up with as your answer. Okay, I hope you paused and took the time to actually figure it out. Ready? The answer is C. All right, so let's look. If I do W and Z together, W and Z, 20 and 50 is 70 seconds, and X and Y is 75. So if I break it up this way, I know it takes me at least 75 seconds because I always got to go with the longest of the two. So remember, C is 75. If I break it up like A says, W and X, so 20 and 30 is 50, that looks good. But Y and Z are 95. Well, 95 is not less than 75, so that's not a good option. For B, W and Y, 20 and 45 is 65. That looks good. But 30 and 50 for X and Z is 80. 80 is not less than 75, so C is still winning. If I leave Z alone, that's 50 seconds, that's okay. But if I put these together, 20, 30, and 45, that's 95 seconds. Definitely not better. So that is why C is our answer. All right, well, there's more practice available in AP Classroom, but for now, I think it's time to do a Create PT tip of the day. So one of the program code requirements is that you must write a procedure. It must be student developed, meaning you need to create it. And that doesn't mean just writing the code. You cannot just write the code for something that is an event handler or a main method. You need to define the name of the procedure, everything from start to finish. The procedure also needs at least one parameter. That parameter must be used in the procedure. So just giving it a parameter and never using it in the procedure doesn't count. Okay. So you're going to need to make a procedure, and that procedure must use at least one parameter. That parameter should somehow affect how the code is executed within the procedure. You will see as you continue with the written responses that in part D, you need to give different calls to the procedure. They can be hypothetical calls. They don't have to be calls that are actually in your code. But for instance, if my procedure was called with this value for the parameter, and then you could talk about what happens. You need to be able to show two cases, two different cases, two different values of the parameter where one part of the code is executed in one and a different part of the code is executed in the other. So hopefully that helps you a little bit as you are getting ready and finalizing your create performance tasks. Once again, I want to remind you that we have this link here. You can type that URL into the computer. It will take you to a Google folder, and inside of it is a create performance task information sheet that has information about the rubrics, the details of the instructions. Any tip we are covering is from those instructions, just a little less wordy. But make sure you go through and read through them carefully. And also don't forget to read through those rubrics. There's some really nice videos that you can also use to help solidify all this information. So what are we going to take away from today? Well, I hope that you're going to be able to say how computing devices work together in a network, how the internet works, how data are sent through the internet via packets, and understand the difference between the internet and the World Wide Web. I also hope that you know that for fault tolerant systems like the internet, you can describe the benefits, what makes the system fault tolerant, and identify vulnerabilities to failure in the system. What might be the path that would destroy it if it were to disappear? And then I hope you understand a little bit better about sequential, parallel, and distributed computing. In other words, being able to prepare to compare problem solutions and look at the efficiencies of the solutions. Thank you so much for coming today. I'm really excited that you are here, and I hope that you're going to come back and watch more of our review videos. I am really happy to hear that you are studying computer science principles, and the fact that you are watching these videos tells me that you are invested and you are going to do really well. So keep on keeping on. Do a great job in your class, but also put your time and effort into studying. I know you can do it. But now give yourself a break. Thanks for watching. Go out now and have some fun with computer science.